In the last video, we saw how NPCs find if a path is clear, but not how they find the path to go on. If the place an NPC wants to go is in clear view, then the path is quite simply 2 points. If the goal position is hidden behind something though, and the local navigation system couldn't sidestep it, then we need something else to find how to reach our goal. In the level editor, Hammer, level designers place these sort of markers that are invisible in-game. These are called nodes. The word node means a place where two pathways meet. Nodes essentially tell an NPC, hey, this is a place where you can go, and the NPC trusts that the node is right. But wait, why would we trust that if we didn't use our MoveProbe going anywhere to or from that node? Well, you see, somebody else already did. Okay, before we explain that, we have to talk about holes again. You may have heard some things in videos about Half-Life 1 or Quake, really just Quake, honestly, about how collision detection depends on Minkowski distances and everything having to have specific dimensions and baking a bunch of collision data into the map file. None of that applies to Source. In Source, anything can be pretty much any size. The only place where any of that arcane logic still exists is in AI navigation, ironically. We're going to be doing more tracing work, but this time our work has to account for all kinds of NPCs, not just one whose hole we already knew. We can't just do our traces again and again for every single hole size that could ever exist, as there are infinitely many, so we'll limit ourselves to 10 different sets of dimensions. Tiny-centered, tiny, human, small-centered, wide-human, medium, medium-tall, wide-short, large-centered, and large. Almost all of our work will be done 10 times, once for each hole. Every NPC's hole has to fit one of these sets of dimensions, or else their navigation queries may bring back an inaccurate result. The exceptions either don't move, at least on their own, only move on pre-designed paths that the level designer ensures will be clear, or are not a real NPC. Only one NPC breaks the rule for a somewhat questionable reason, the Antland Guard. Its hole has to be much larger because it simply is much larger. Even though it doesn't match, they still navigate as if they have a large type hole. Originally, I was going to say that I can't recall the Antland Guard ever having problems moving around, but then it moved weirdly twice in this one clip, so... For every ground node and for every hole, a flat downward trace is done to find where an NPC with the given hole would stand above or below the node. This lets us know precisely where NPCs will be when they're horizontally centered on the node. They won't always sit perfectly on the node because sometimes one side of the node will be at a different elevation than the other, meaning each hole sits at a slightly different height, or the node may not rest on the ground. This is almost the same thing as the floor point check from the first video. These traces will pass through things that could be moved out of the way, like doors or whatever other clutter is lying around. When an NPC's MoveProbe is doing the real traces, it will be blocked by those things, but for now, we assume those things will move out of the way at some point. Climbing nodes have their own tracing process, but it's not very interesting and I don't want to talk about it. Air nodes do absolutely nothing at this point in code. Next, each node looks at every other node to see if they neighbor one another. For two nodes to be neighbors, they must be within 720 units of each other if they're climbing or ground nodes, or 1440 units if either is an air node. Then up to 4 line traces are done between the two nodes. The first one goes from where a small centered hole would lie on one node to where the same hole would lie on the other node. If this line hits something, then it's tried again with both points raised 70 units in the air. If that line also hits something, then it tries going low and high and low. If at least one line had a clear path, then they're neighbors. These lines have the ability to go through all entities except the world. To avoid forming unuseful connections between nodes, all nodes compare their neighbors to one another. Air nodes are not compared to nodes of another type. Climb nodes won't bother comparing neighbors that are also climb nodes, only ground nodes to other ground nodes. If the lines to the neighbors from the node form an angle that's less than 22.5 degrees, the node which is farther away will not be considered a neighbor. If both nodes are equally close, it comes down to the order of the nodes in memory. This means that two node graphs with identical node placements could produce different connections based solely on an invisible order. This should never happen, but it could be worse. When the game decides to revoke neighbor status from a node, it does so asymmetrically, as in the node revoking it will no longer recognize that other node as a neighbor, but the other node will still consider it to be a neighbor. If that node comes earlier in memory and it did not also find a pair of neighbors that causes it to revoke the neighbor status from the first node, then the nodes will stay connected. Now we start doing traces to verify that the nodes can be stood at and the links we've drawn between them can be traversed. Doing that requires heavy use of a MoveProbe, but MoveProbes are inherently tied to the NPC that created them because MoveProbes refer to the properties of their NPC on several occasions. You can't have a MoveProbe without an NPC, so we make an NPC called AI Test Hole and use its MoveProbe on every node and the paths between them, once for each hole. We already went over how the MoveProbe works in the first video, so there's not much to say here. If two ground nodes cannot reach each other by walking, we only then try jumping between them. It is recorded whether or not links and nodes are accessible for every hole. If a link can't be traversed with any hole, it is discarded. To test every hole, the AI Test Hole NPC's hole will be changed as needed. AI Test Hole's maximum jump, rise, distance, and fall are all 1024. Every node has a number assigned to it which is called its zone. Every node's zone is initialized to 0. Nodes that have no links to other nodes have the zone number 1. Every node which still has a zone number 0 will be assigned a new zone number starting at 4. The number 2 is unused and does not mean anything special, and 3 is only used for development purposes. Then it looks at the nodes it links to and does the same for them if their zone is 0. This causes the game to iterate on nodes in groups based on their connectivity. Because of the way the code is structured, it is certain that it won't start iterating on nodes that are unconnected to that group until it is iterated on every member of the group. We're also able to know exactly when we start iterating on a new group, so at that point we increment the number we assign to the nodes. This means every group of nodes that share any connection to each other along the graph of nodes will share the same zone number. This includes nodes that are connected by jumping and climbing. And that is how you build a node graph. When a map is started and the node graph is out of date, it rebuilds it, which is when you get the famous message. The game automatically detects if the node graph is out of date at the start of the map without any user input. Detecting that the node graph is out of date involves several different things, but the most important one is the date of the map file and the date of the separate file that the data about the node graph is written out to. If the two dates don't match, it rebuilds the node graph. The only other factor that's particularly pertinent is that the file version numbers match. When a map is being made in Hammer, a hidden version number in the VMF is incremented when saves are made. This number is carried into the BSP file, and when the node graph is built, it records the version number of the BSP that the graph was built on. If the version numbers don't match, then the graph needs to be rebuilt. This check is only done if the file dates match, which is really backwards if you think about it. Distinct from nodes is another class of invisible markers to help NPCs called hints. Hints can do many different things and give NPCs additional context about their surroundings. There exists an overlap in the form of hint nodes. Hint nodes give NPCs additional context about how to navigate. The many different things that hints can do are not really worth going over individually because most of them are rather minor, but there is one I have to mention because I said I would. There is one type of hint node that allows any NPC to jump from it to a hint node of the same type. This is how NPCs besides antlions, fast zombies, and hunters are sometimes allowed to jump. Okay, so we know if a node is usable thanks to the work of an ancient unknowable entity. So now the question is, how do we use the node graph? If local navigation can't serve our needs, the NPC will then try finding a path through nodes. Notably, striders are not able to use local navigation, only nodes. First, we find the node closest to the start and end position each. Before doing anything complex, we check the zone numbers of those nodes. If the two nodes don't have the same zone number, then we know for certain that no path exists between them. If either node's zone is 1, then that node is isolated away from all the others and no path can exist involving it. At this point, we're all ready to start the real pathfinding. Source uses an A-star search algorithm. If you've ever looked into pathfinding algorithms before, you've probably only seen examples done on a grid and with some simplifications. This is a real case, and as such, it won't work quite the same, so just keep that in mind. That, and Valve just wrote it a little weirdly for reasons we'll never know. The algorithm starts by creating 6 lists that will be used to record different properties of every node. One value is the node's parent node, which will be the node that we're trying to reach the given node from. Two properties are if a node is open and closed. Being open means we're interested in looking at if the node is useful for our path. Being closed means we've marked the node as open at some point in the past. A node can be open and closed at the same time. Wait a minute, that's nonsense. I'll instead just say that nodes can be on both the open list and the closed list at the same time. The final three properties are a node's f, g, and h values. The f value is simply the g value plus the h value. The g value is the given node's distance from the starting node along the path we're attempting to form, not the direct distance between the two nodes. The h value is the direct distance between the given node and the ending node. The g value of every node is initially a very large number which is used to represent infinity. The starting node's g value is 0. Its h value, and therefore its f value as well, is 1/10 of what a node's h value would normally be. I will explain that later. The starting node is added to both the open list and the closed list. Now the code enters a while loop whose only condition is that there's at least one node in the open list. If there's not any node in the open list, then every relevant node has been tried. The loop starts by finding the node which has the lowest f value of the ones in the open list. On the first iteration, this will of course only be the starting node. That node is then removed from the open list. If the node being looked at is the ending node, then we reached the end. Now we iterate on every link the node has to another node. The game first verifies in multiple ways that the link is usable. Most of that code is truthfully not very interesting, though we do see a return of is jump legal. Then we find the cost of the link. A link's cost tells us how favorable or unfavorable it is to move from the start to the end of the link. This is based mainly on the distance between the two nodes. The longer the distance, the higher the cost. If the NPC has to jump or climb between the two nodes, the cost is doubled. From there, individual NPC classes can modify the cost further. Fast zombies multiply the cost by 0.5 if they'll be jumping downward and 1.5 if it's upward or to a place of the same elevation. They also multiply the cost by 0.5 when climbing upward and by 4 if climbing downward or horizontally, but that never happens. Player companions, which is these guys, when trying to avoid attacks from snipers or the suppression device, will multiply the cost by 1.5 if the link would take them towards the center of the danger. I would guess this prevents cases where they would try to avoid the danger by running across it. They also multiply the cost by 0.1 if going along the link would put them behind cover from the suppression device or sniper. If the neighbor node is not in the closed list, we accept it as a node that might be worth exploring. If the neighbor is in the closed list, then we must have already looked at it, or we already plan to look at it anyway. Even if the neighbor is in the closed list, we will reconsider it if our node's g value plus the link's cost is lower than the neighbor's g value. It's at this point in code that we record the neighbor's parent as our given node, set its g value to the given node's g value plus the cost, set its h value to the direct distance from the neighbor to the end node, set its f value to g plus h, and add it into both the open list and the closed list. Now about that h value on the starting node. As you saw, when we're calculating the cost of a link, we're usually doing the same thing as when we calculate an h value, but not always. We can't have parity because we don't know anything about how we would travel on a straight line between two nodes when they don't actually share a link. We don't even know what type of movement we would do. This opens up the possibility of taking a path that's not truly the most ideal, at least from a technical standpoint. This goes into some very open-ended territory, and the best thing to do about it has to be decided on a case-by-case basis. Still, we'd rather have h values that are lower than what's actually possible. Overestimating them means we risk forming an unoptimal path, while underestimating means we risk being less efficient. The latter is very much preferable. This is my best guess at least as to why the starting node's h value is 1/10 of what it would normally be. Here's a recreation of how this particular search plays out. The open node with the lowest f value is 108, so we look at its links now. Eventually we should find that we're iterating on the ending node, which means we found a path, and with how we're using the open and closed lists, we're searching through the nodes in an informed and efficient way. If we do run out of nodes in the open list though, then there's no viable path. It's important to understand that we only declare the path found once we iterate onto the goal node. That is, when we find that it's the node with the lowest f value in the open list, not just the moment we find a link that connects us to it. If we were to do that, then we wouldn't be considering the cost of the final link, which means there could be an alternate path with a lower total cost. To find the sequence of nodes we'll take, we look at the goal node's parent and then look at that node's parent recursively until we reach the starting node. I found it hard to make a good example in Half-Life 2. If you want to see some other examples, the GOAT has a video on it. Are you ready? Let's move. An NPC remembers where to go using a data structure called a waypoint. When using local navigation, there's usually only one waypoint in the path, that being the one at the goal position. A more complex path will have multiple waypoints though. Sets of waypoints exist in a linked list, so every waypoint only knows who is before it in the path and who is after it. When moving, the NPC focuses mainly on getting to the next waypoint in its path. Movement animations in Source include a full walk cycle which was made not with the character running in place, but with the overall motion included. The entity in-game looks at how the model's root bone moves to decide how fast to move. This means as long as the character was animated well originally, there will never be any problem with the character's movement looking too fast or too slow when compared to its animation. To keep the model from running away from its origin, an offset of some kind is applied to the model, but I couldn't find the code responsible. The code that manages how NPCs move when actually moving is also called local navigation, but it's entirely separate code from that which we saw in the first video, aside from the MoveProbe. There's some code that allows NPCs to find a path they can take around small obstacles that may block their way. It's more or less the same idea as the code from the first video, so it's not really worth going over. If an NPC is blocked by a door that it can open, it will still proceed down the path, and when it reaches the door, it will open it. The NPC will know when to open the door because a waypoint will keep a note of this. If a Metro Cop is in combat while holding a stun stick and it's blocked by one of these things and it's breakable, it will hit the object until it breaks. Player companions will tell other NPCs to move out of the way if the other NPC is blocking it. Antlions also do this only to each other. As for everyone else, I guess they're just out of luck when it comes to being blocked by an NPC. These NPCs may also simply decide to ignore the blocking object if it's physically simulated and its mass and size are within certain limits. In this case, the NPC will simply push the object out of the way as it walks. Since nodes can only represent so many positions, NPCs would move rigid and unnaturally if they were forced to stick strictly onto them. If the waypoints meet certain conditions, they can be repositioned or taken out entirely to create a more simple and natural path. I'll refrain from bogging this section down with too many details because they're not that interesting. The NPC will use its MoveProbe to see if it could go to the waypoint after the one it's currently heading towards. If that path turns out to be clear, it takes that one instead. If that waypoint is far enough away from the current waypoint, it will try going to points along the path between those two waypoints. If you've ever seen Half-Life 2 speedruns, then you've surely seen the trick where putting something on an NPC's head while they're moving will make them teleport. What makes this work? As we saw in the first video, pretty much all you have to do to get an NPC's MoveProbe to say it can't move is put something on top of its hole. The NPC teleports when the object is inside its hole. Why is it able to actually intersect the hole? I don't know, that's just how it works. But wait, NPCs are supposed to push things out of their holes when that happens. They do this when standing still, so why not when moving? When using the MoveProbe while moving and an obstruction comes up, the NPC will consider its path to be clear if it can find a way to sidestep it. If the probe comes back good, the NPC will remember that there is nothing blocking it, with the idea being that we're not really blocked if we can just move around an obstruction. Now, even though their movement looks smooth, NPCs really teleport from location to location. To find the exact spot on the floor to teleport to, the NPC will use the MoveProbe again over a very short distance. As far as I can see, this is the only reason for using the MoveProbe a second time. It shouldn't be necessary to actually verify that the path is clear again because that was already done just a moment ago. Even if we're sidestepping something, we're tracing on the path that we're going to take around it, not the original path. In any case, this tracing should have already been done. This should be completely redundant. Still, for reasons I couldn't figure out after a very long time spent searching, this probe actually can fail somehow, and Valve actually did care about that for some reason. If the first navigation query comes back negative, or if it came back positive but the second query came back negative, this is when the NPC will recognize that it's stuck and start considering how to approach the issue. If an NPC has found that it wasn't able to move along a node link, it may mark that link as being stale. This will tip off the NPC and any other NPCs that they may want to avoid the link. Other NPCs who try the link later on will unmark it as stale if they find that it's since become clear. However, when an NPC is moving to a scripted location, the waypoint is usually not associated with any node. It's usually moving to an invisible entity. No node means there are no links to mark as stale. If there were links to mark, then the NPC may go on to find an alternate path through the node graph. No links marked means we would simply generate the original path again. In this case, or the case that there simply is not an alternate viable path, the NPC has to try something else. First of all, only these NPCs are allowed to teleport in this way, and they have to be in a scripted scene. Otherwise, their movement is not considered vital enough to justify extreme measures. If we stored in memory a pointer to an entity that was blocking us, we'll try now to push it out of ourselves as long as the blocking object is not the world, the player, an NPC, or Funk Track Train. The problem is, only the first test records what entity was blocking it, not the second one. So in the NPC's eyes, it has nothing to push away. This means the NPC only has one option left, to teleport. The NPC tries to teleport to the waypoint it's currently trying to reach. The NPC will first verify that the waypoint is free of obstructions with the following: a floor point check, which is only to find the ground and does not need to be passed, a stationary hole trace on the place the floor point check hit, and a stand check. The stationary hole trace must not find anything inside it, and the stand check must pass in order to teleport to the waypoint. If either reveals that the waypoint is not suitable, then the NPC will try waypoints further and further down the path until it's tried them all. If there are no suitable waypoints, then the NPC has no response. I would too, like, what the fuck?